Okay, so how does our classification model determine whether we have a positive class output of 1 or a negative class output of 0? We can use our sigmoid function or a logistic regression model to be able to visualize how this happens. So we can see that when we're on this side of the graph, our function is going to output these values. And when we're on this side of the graph, that function is going to output on these values. But it actually turns out when the output is on this side, it'll actually just round up to 1. And when the output is on this side, it'll just round down to 0. So in other words, when our function is greater than or equal to 0.5, or z, which is our x value, is greater than or equal to 0, our model is going to output 1. In contrast, when our model is less than 0.5, or z is less than 0, our model will output 0. And you can see basically that this box right here models this scenario, and this box right here models that scenario. Now, of course, it goes on infinitely this way and infinitely that way. So just like in linear regression, in logistic regression, we'll have multiple parameters as well. We'll continue to have this model, and we can rewrite it as this. So here we have two features, and the vector parameter w and b, which is another parameter. So let's just say, just like in linear regression, how we initialize our parameters to set values initially, we'll initialize our parameters here to set values initially. So let's pretend w1 is equal to w2, which is equal to 1. So they're both equal to 1, and b is equal to -3. So what we're going to do is we're going to set z, or our vector here, vector w, times our vector x plus b, which is the same thing as this, remember, it's vectors. We'll set it to 0. And the reason we do this is we can see that when z is 0, we actually divide our logistic regression model here. We divide it, right? On the x, when z is greater than 0, we have output that's 1, and when z is less than 0, we have output that's 0. So we'll set this equals 0. And this is actually going to be our decision boundary. So if it's less than our decision boundary, we're going to assume that our model y hat predicts 0, and if it's greater, y hat will be 1. So we can simplify this. And this is just because we said that w1 equals w2 equals 1 and b is equal to -3. So we just substituted the values. And we can rewrite this as x1 plus x2 is equal to 3. So this is our decision boundary. And we can see that this decision boundary actually works pretty well for a data set like this. x1 plus x2 is equal to 3. Graphs align just like this. So we said values greater than it will be y hat is equal to 1. And we said values less than it means our model will predict it to be 0. Note though, if we had a different choice of parameters, if our values w1, w2, and b weren't, 1, 1, and -3, then our decision boundary, our line, might have looked completely different, and it might have not categorized the data as well. It might have looked something like that. And in that case, we would have to readjust our parameters so that our decision boundary better divides these data points into their respective clusters, which is what classification is. But what happens when we don't want a linear boundary? Let me show you what I mean. What if our data set looks something like that? You see how it's like separated by almost a circle, right? So we have this inside cluster here that should be paired into, we'll say that this is y hat is equal to 0. And we have this other cluster over here on the outside, and we'll say that this is y hat is equal to 1. So remember polynomial regression? We can do this with logistic regression too. We can have like x squared values and stuff like that in our logistic regression model. So we can write this as, remember, we'll have x squared terms here too, so that we can fit this decision boundary to a circle or a curve. So that's why I'm squaring our features here. Okay, and let's say we choose the parameter values 1, 1, and -1. So we assign initially w1 to 1, and w2 to 1, and b to -1. So our z is equal to x1 squared plus x2 squared. Remember, just substituting the values here. And we'll set this again equal to 0. And if we rewrite this, we'll get our decision boundary. And this is actually a circle with radius 1. So just like this right here. So a perfect decision boundary. And of course, this is an ideal case. In reality, we'd have to iteratively change our parameters so that our decision boundary is optimal. But in this case, we'll just assume it was optimal right off the bat. Okay, so we can see that, hey, it's done a pretty good job of dividing our data. And we can say that if our values are greater than our decision boundary, so if x1 squared plus x2 squared is greater than or equal to 1, we'll assign that here and say it'll predict a value of 1. Or, in contrast, if our data points are as follows, where x1 squared plus x2 squared is less than 1, then we'll give it a y hat value of 0 on the inside over here. And there are even stranger cases as well, where our decision boundary might be an ellipse. So this like elongated circle, or even a weird shape. I don't even know what you would call this shape right over here. It looks like an animal or a truck, but you know, we might have some certain clusters over here, and then some certain clusters outside it over here that fall into two separate categories. So a decision boundary like this, regardless of how it looks, might actually be optimal in these situations. And you can get these weird decision boundaries by using higher polynomial terms, such as these over here. We went to like x cubed here, right? So using all these weird and higher polynomial terms rather than just like x1, x2, and not squaring it or square rooting it or anything like that. And we'll get these weird curves, which might be good or might be bad for certain scenarios. So note that if you're to not include higher level polynomials and just included x1, x2, x3, not x squared or something like that, your decision boundary for logistic regression will always be linear. So something like that, right? A line, and not a curve or some weird elongated ellipse or whatever that is over there. So just note that. Okay, hopefully you guys enjoyed this video.